first I have to tell you what phase field model is a little bit more and how we solve them. So I'm going to give you a very quick overview. Actually, PRISMS-PF ended up to be, we started out, we set out to develop a computationally efficient tool to solve phase field model, phase field equations. But it ended up to be actually pretty general and then actually very useful for many different kinds of partial differential equations. So I'll try to make the point, and then I want everybody to have some experience in installing this type of software. So I sent a note last night about how to install some of the kind of prerequisite. I'll talk about that, and then we'll have some interactive time. So, okay. First of all, Docker is a tool. It's a kind of like you can install software in a way that it has all the kind of prerequisites. Unfortunately, a lot of the open source code uses other software frameworks, right? So because of that, there's a lot of dependencies. That's why we use Docker here to make that easier, so you don't have to see all those nitty-gritty, because often it fails. You try to install things from the scratch, and it doesn't work. And so anyway, so we use Docker. Another thing we need is Visit. You could also use Paraview, but we tend to use Visit for visualization. So it's that. And then another thing that takes a bit of time is Poland, the PRISMS-PF software framework. So if you haven't done those things, please just start it and then kind of keep an eye on it just to make sure it's actually downloading and download it. Okay, so so if you need to do that, see the email for links and comments. And then we found out today that there's some kind of problem with the server that is that has a 3.4 version for at least Mac. So try 3.3 if you are getting like a failure. So like it may try to download up to a certain point, and then it might kind of like die, right? And so in that case, try 3.3. Okay, so phase field model has a lot of different applications. It can be used for solid-solid phase transformations, like those are examples. Liquid-solid phase transformations, so those are the examples. Left-hand side is from my group, and then right side is our University of Michigan group, and then on right side is like external groups that are actually using our software. In the more recent times, we've been actually using it to follow interfaces as they evolve with time due to electrochemical reactions. Okay, so the idea behind the phase field model is like this. So it's really basically the combination of thermodynamics and kinetics. So, but the key point here is that when you have microstructure, the microstructure may be very complex, and then sometimes pinching might happen, or new surface might appear because of nucleation. And these things are really hard to deal with if you are to keep track of sharp interface. Mesh interface, right? And then sometimes, those mesh points can get tangled up because they overshoot and then get, crossed against each other. So nice thing about diffuse interface is that these things kind of naturally happens, right? Like pinching happens naturally. And when something disappears or something is created, it's kind of, it's very well regularized because of the fact that you have this kind of diffuse interface. It gives this length scale that by which the system is regularized. So and then so you have bulk quantity. It could be density. It could be order of the system. It could be concentration. And you have those bulk quantity in one phase versus another phase. And then there's this diffuse interface region where the bulk quantities change relatively smoothly. Meaning, it can't be too rapid because you want to be able to numerically resolve it. But you also don't want it to be too broad because then you don't actually have the bulk, right? So this is the kind of like there's a trade-off there. But once you have that, happy, medium, you got this partial differential equation that describes the evolution of the system. And you can solve this partial differential equation everywhere in the volume. So if you are looking at represented volume in the microstructure, in a solid or liquid or whatever, then you can just assume, like a periodic boundary condition, and you can solve the equation everywhere, and not worry about where the interfaces are. So you eliminate this need to explicitly track the interface. And order parameter is a term that's used in describing any quantities that are being kept track of in phase field model. And what they are depends on what you're studying. So if you have order disorder transition, you have like, here's a green A atom and red B atom, right? And so here, they are randomly blended, right? Whereas like here, there is a pattern. But overall, the average composition is not changing. So this transition can happen without worrying about something needing to diffuse long range. Whereas in this case here, again, this and this looks the same, but say A likes A, B likes B, A doesn't like B, then this is what happens, right? This is a non-ideal interaction that gives rise to phase separation. And for these cases, you sometimes see something called spinodal decomposition, so that the system kind of decomposes into two phases. So in this case, though, you need to move red atom on this side to this side, whereas green atom from this side to that side. That requires diffusion. And that means that as you solve this equation, as you change the concentration of this system, that it's a concentration, and you have to make sure that that quantity is conserved. So it depends, depending on if the order parameter is conserved quantity or non-conserved quantity, you actually have a different partial differential equation that you have to solve, and I'll mention it later on. Okay, so this is a conserved order parameter case. So this phi here is related to concentration. So let's look at this kind of simple silver copper system. And it's got the FCC structure. And there are two stable phases. One is silver rich, and the other one is copper rich. Okay? And then this barrier between the two indicates that copper atom and silver atom don't like each other, right? So if you try to force them to be together, it's unhappy. It goes, energy gets higher, right? But if you can let some of them through, and then so a little bit of copper in silver is actually good. A little bit of silver in what did I say? A little bit of silver in copper is good, and then vice versa here, right? So and you can get, so this will give us free energy. You can get this type of data actually from databases now. They can be, it's usually from experiments, and really, they're just reproducing the equilibrium point, right? Instead of like really knowing what the shape of this is. But you can still get them from databases, and you can actually stick this into the bulk free energy term of free energy density term of the free energy function for the system. Now, in practice, it often doesn't really matter what shape this is, a little bit different. So sometimes we use something simplified like this, where there are two equilibrium points and kind of nice, nice. This is a quadratic function that allows you to take derivatives and things like that very easy. And then you can also shift the point of the equilibrium. So this is actually not quite 0 or 1, but you can do this, right? You can subtract from concentration an equilibrium point divided by the difference of the concentration from here, and then that will let you go from 0 to 1. So, using that, you get something more like this, where equilibrium value is going to be 0 and 1. However, if you just have this, the lowest energy state is just the one value, 0, and then the other value is 1, right? So there's going to be a sharp interface. So one more term is needed. This is this gradient energy term. What it does, so if the gradient gets really high, the value goes up, right? So it's a penalty for sharp gradient. And the balance between this term and this term gives rise to this well-controlled interfacial thickness that allows you to calculate the curvature, allows you to calculate, obtain the right dependence of the chemical potential on curvature to reproduce Gibbs-Thompson effect. So these are the terms that goes in. Once you have this free energy, you can calculate the chemical potential. Chemical potential has come up so many times, so I think people are already familiar with it. But just to make sure, if there's a change in chemical potential, there's going to be a driving force towards chemical transport. So if there's a gradient that's not 0, then there's going to be a flux. And mobility is going to tell you how easily the species can respond to the driving force. And then negative is going to tell you you're going to go down the gradient, right, down the hill. And then we also have the mass conservation equation. So if you have the flux, the divergence is going to tell you what goes out minus what comes in. So minus that is going to give you how much is going to contribute to the accumulation. So, and then I already mentioned the chemical potential looks like this. Combining all that, you end up getting this equation. And this is a classical Cahn-Hilliard equation and describes spinor decomposition. If you start the system with concentration in the range of spinoro, within the spinoro region, and then if you start out with some other range, you'd have a nucleation growth that would be reproduced by solving this equation. Another type of equation, I mentioned there's a conserved, right? So this is a conserved case. Sorry, yeah, there. And the non-conserved case is quite similar, but the evolution of the order parameter doesn't really need this, what comes in minus what goes out it gives the right to change. No, this is just proportional to the chemical potential. And again, still down, and then there's some coefficient that tells you how quickly the system can respond to the driving force. And if you put in this free energy, you get this equation. Again, there's that term coming from the gradient energy. And you just solve this, and then I'm going to use this equation later on to illustrate how it gets solved in a finite element framework. Any questions? Okay, good. So, we are at the University of Michigan. One of the projects I've been involved for a long, long time is PRISMS Center for Predictive Integrated Structural Material Science. And then our focus is to study magnesium and their mechanical behavior. But mechanical behavior is really affected by the microstructure. So, and then science is part of this center, but also software development is a major part of it. So PRISMS-PF is one of the software we develop. And it is based on the DIR2 finite element library, which uses a matrix-free finite element approach. It's not just for the phase field model. We have fluid dynamics module because sometimes if you're studying solidification, you don't have fluid in there. But there are many capabilities here, including adaptive meshing and multi-level parallelism. That makes it really, really high performance. We also try to make it as easy as possible for the community to use. So we try to keep the interface to be simple. And we have a detailed online user guide. We have pre-built applications, two of which you'll try today. Docker-based installation, which you're going to try today. We have other things that are integrated as well. YouTube channel too. So actually, just to acknowledge David Montiel is the lead developer of this PRISMS-PF. I'm the faculty lead. The director of the center is John Addison. He's been very much involved in this effort. My group typically is participating in some way, developing cores for other project purposes, but then they also give it back by packaging it as an application. And then there are other external collaborators now who are also developing the applications using PRISMS-PF. One thing I wanted to really highlight is the performance of PRISMS-PF. I used to, be kind of like more brute force numerical person. So like finite, difference, implementation with, using many CPUs, right? And that's easy to teach students, easy to develop cores, etc. So we had a whole bunch of finite difference cores. And then we compared it. I was kind of skeptical with a finite element method to start with. And then indeed, if you just leave the mesh to be regular, so the same mesh size everywhere, then you don't get much of a speed up. But really where we get the major acceleration is the adaptive mesh. So you can, with phase model, you have this regions where, near the interface where the function is changing very rapidly. So you can mesh those areas very, finely, and then not so much away from there. So we got like, more than 1 order of magnitude speed up. And this is really, significant, right? Because, there were some simulations that we were running using the finite difference code that took like 2 weeks, right? So that 2 weeks run is going to be like 1 day. And then that makes a huge difference in terms of throughput for our, results. And then we also compare with other software as well. And then you can see their benchmarks available. And then NIST has something called a PF hub that posts all these benchmarking results. And we are pretty competitive to other software. More recently, and we've been like making it faster and faster by really, Jason especially, who is here, he's been working on making PRISMS-PF more computationally efficient. So typically when you see GPU codes, they're like so much faster, like forget it, we are not going to be able to compete. But we recently collaborated with Alain Kama's group from Northeastern, and we compared it very, very carefully, that we're making sure we are getting the same results, etc. And we actually ended up to be not terrible. I mean, we won't beat a GPU, but we were able to get up to like, quarter, which is not bad. Like, so we are still slower. The GPU is faster by about a factor of 4, but it's not orders of magnitude. So we were very happy, and then actually, Alain Kama was quite impressed by what PRISMS-PF can do, especially given that this is open source code. Publicly available. Okay, and so any questions? Yes?
How GPU-able is your code?
What do you mean?
Is it possible to parallelize your code so that you run some GPUs, or because
it is possible. It is possible. The reason we are kind of holding off right now is that we are working with the DIR2, which is it's a finite element library. And they are switching the GPU. So, the GPU coding used to be like, you have to specifically code to specific GPUs, but they're switching to a more generic one where that will work for many different GPU platforms. So and then they're doing the switch right now. I think actually we can do better testing of it. So I think Jason might actually be there might be something on his to-do list already. But yes, it is something that we want to do, and we are planning to do shortly. But we didn't want to develop a code specific to certain GPUs, and then now that seems to be resolved. So we are going to try to take advantage of that. Okay, so this is. I'm just going to show you how to. If anybody is interested in solving the equation, any kind of equation, I'm thinking of a hackathon on that coming up later this semester. So I'm going to just use this as an example. So you have a time derivative, and then you have the expression on the right-hand side, which also has this term that involves Laplacian. So to implement that, first what you do is you discretize in time, and you get something that looks like this, where this is the future time, right? So first thing you discretize, just like near approximation, and then solve for the future value. So this is everything on the right-hand side. This is explicit methods. Everything on the right-hand side is from what we know now. This is the future value. You have to figure out what it is. And so just for Euler, there are other methods that can be used, and just change the expression a little bit, right? And then finite difference, and this is now in space. You have to discretize in space. You can do finite difference and solve the equation, no problem. But in this particular case, we use finite element method. And nice thing is that you can have adaptive mesh, and geometry can be flexible. And then finite volume, I think Jorgen talked about, right? So, and general idea for finite element method is that you have like bases within each element, and then you can represent the function as a linear combination of the bases. And then, so you have that. You have the partial differential equation. And then you multiply the partial differential equation with the weight function. And the weight function could be the same thing as the same function as the basis function, but it doesn't have to be. And if basically you use that to discretize the continuous equation, and you integrate it, and then those integration over each element is related to integration on each element of other parts. So, and then there's going to be a sum over there in here, and then you can figure out, you can just kind of work it out. I have like a kind of like a step-by-step instruction of how to derive it into discretized form. And at the end, what you get is a matrix equation. And but for the implementation, for the if you are to change the equation in PRISMS-PF, what you want is just the weak form. So you start with the equation. So that's the left-hand side is unknown. That's the future value. And the right side is everything that we know. And then you, wherever you have the grad term, you integrate by parts. And you get some expressions. And at the end, what you want, and then the surface term goes away because of the divergence theorem and the choice of the basis function. And at the end, you get something like this. And this part that multiplies the test function is called value term. And that becomes something that you type into the equation.cc of the PRISMS-PF file. This part here that multiplies the grad test function is called the gradient term. And then that goes into another part of the equation.cc. So these are the input that goes into PRISMS-PF. And then that's really what you have to do. You have to also set the bound. In terms of changing the equation, you have to also define the initial condition. You have to also set the boundary condition. And then in general, that should be it. So PRISM-PF is something that we are still developing. This is, it gets better and better, and we have more and more applications. Applications are nice because it gives you an example how you implement certain partial differential equation. We have 3.0 available, but today we are just going to stick with 2.4 because it's the Docker implementation is available. Okay, and then new and upcoming features. We have YouTube video tutorials. We have integration tools. If you want to do polycrystalline, if you want to include polycrystalline microstructure, you can take it from Dream 3D, create it, and then input it into PRISMS-PF. We have post-processing scripts, and we also have materials commons is our repository, and then there's a way to connect to it directly. And also that you can connect with other tools. So right now, crystal plasticity code exists, and there's an active development that tightly integrate the phase field and crystal plasticity. Okay, and community support, there's online user manual, message board, and community practice. And we are really growing in user base. So this is unique clones. Actually, the PRISM-PF is a green part, which is actually biggest out of all the tools that we have. Yeah.
So when you put it into weak form, you then numerically solve it in weak form?
It's taken care of. It will be solved, but it's actually taken care of in the software itself.
But is the software is the algorithm that the software uses designed to work in weak form? That was new to me.
Yep.
Yes.
And what's the motivation for moving this into weak form and solving it there instead of doing?
So weak form is really the basis of finite element method. So if you want to solve equations using finite element method, you have to put it into weak form.
So this is for the sake of the way you discretize your domain, kind of.
Yeah. Mm-hmm. Yep.
Okay. Thank you.
Mm-hmm. Okay, so that's it for the background. Any other questions? Really the background here. Sorry it took too long, but now we can try it. So here, if you go here, there is a GitHub page that tells you step by step what you can do to run it. So either you can do the QR code using your phone and then copy that over to your computer, or type this in. So tinyurl.com, PRISMS-PF-IPAM.